All right, this is our last section of notes for chapter 4. So we're in 4.7 and we're going to talk about inverse trig functions. Back in the beginning of the year, we talked a lot about inverse functions. So I just want to remind you of some of those rules because inverse functions are pretty prominent as far as I've seen so far on our AP test. So remember a couple of rules. If a function has an inverse function, then the function f of x has to pass the horizontal line test. Now, that is not an official reason that you can give on the AP exam. What you have to officially say is f of x is 1 to 1. But in my mind, I'm always thinking horizontal line test. So, for example, here's like a cubic type function, and here's a quadratic type function. Something like this passes the horizontal line test. There is one input for every output, but um, something like a parabola fails the horizontal line test because there are two inputs for each output. So our official phrase for passing the horizontal line test, 1 to 1. So this first function has an inverse function. So I'll say f inverse exists. This function is 1 to 1, whereas this function, f inverse, doesn't exist. So this quadratic is not 1 to 1. And another important item that, again, we looked at a lot during the first quarter was that when you're creating inverse functions or when you're looking at inverse functions and their counterparts, the inputs of f of x become the outputs for f inverse and vice versa. So the domain of f becomes the range of f inverse, and the range of f becomes the domain of f inverse. So before we get into trig, inverse trig functions, let's just kind of practice what we did in the beginning of the year. So find an inverse function for each f of x, give the domain and range for the inverse function. I'm also going to look at domain and range for f because that will help me with the inverse. So first of all, here's f of x. This is a parabola, but we're looking at half of a parabola. So this graph does pass the horizontal line test. Remember, it's x squared graph shifted down 9 units. So we're just looking at half of a parabola. Let's look at the domain and range of f because, again, we'll use that to get our domain and range for the inverse function. So whether you need to sketch the graph or not, this half parabola, we're already given a domain. The domain is 0 to infinity. And the range, because this has been shifted down 9 units, is -9 to infinity. So I can already answer the domain and range for the inverse function. I'll just switch these. So why don't we do that? The domain for the inverse function is going to be -9 to infinity because all of these outputs will become inputs. And the range for f inverse will be what the domain was for f, so 0 to infinity. And then how do we get the inverse equation? So remember, this f of x is like a y equals x squared minus 9. So the inverse operation is to switch x and y in the equation, meaning make this x equals y squared minus 9. That would also change out this statement. Instead of saying all the x's will be greater than or equal to 0, all of the y's will be greater than or equal to 0, which corresponds to our range, right? Solve this for y, so add 9. When you square root both sides of the equation, technically there's a plus or minus here, but remember, we're told in this problem whether the y value should be positive or negative. So if the y's need to be greater than or equal to 0, then I choose the positive. So when I write my inverse equation, it's back to f inverse of x instead of y equals. It's the positive square root of x plus 9. And even though I wrote domain and range here, every time we create a new function, again, it's been a while since we thought about this, but every time we create a new function, remember we write the domain restriction. So x square root of x plus 9 is only for x greater than or equal to -9, which I can get from my domain here, or thinking about the rules for square root functions, how we can only square root a positive. All right, so here's the f inverse equation, and here's the domain and range. Now for a log equation, f of x is equal to the log base 4 of x. First of all, just a quick reminder of what that graph looks like. Remember, it's got 1, 0, and 4, 1. And a log graph looks like this generally. So a log graph passes the horizontal line test. We should remember that an exponential function is the inverse of the log function. So maybe you don't have to do math on this. You might know f inverse. If this is log base 4 of x, f inverse will be 4 to the x, base an exponential with a base 4. But if you want to solve for it, you can. Because this is y equals right now, I would switch it to x equals the log base 4 of y. If I want to get rid of a logarithm, I can write both sides as base 4. And the property on the right, 4 to the log base 4, cancels out. So that's another way to get that y equals 4 to the x. So again, f inverse is that. And then what about domain and range? So an exponential function doesn't have any domain restrictions, but it does have a domain. We can list out what it is. So domain of f inverse, range of f inverse. Remember, you can get this two ways. If f inverse is an equation that you know the domain and range of, you can answer that. So domain is all reals. Range, remember this has a horizontal asymptote at 0, and then it does one of these, goes up from there. So the range is 0 to infinity. But remember, you can get that from the logarithm graph too. I've got the logarithm graphed. The domain of the logarithm is 0 to infinity, so that became the range. And the range of the log graph is all reals, and that became the domain. So there are two ways that you can tackle domain and range of the inverse function. All right, now on to trig. So a regular sine graph and a regular cosine graph graphed across all real numbers would fail the horizontal line test. You've got all kinds of places where multiple inputs give you the same output. But if we say, look at y equals sine x and just graph this section, that section's kind of highlighted for you here. This section does pass the horizontal line test if you're not graphing the rest of it. So just like we can graph a half parabola and find an inverse function, we can graph a section of the sine curve and find an inverse function for that. So let's just look at this. Let's look at y equals sine x. I want to write this down here. Actually, I want to write this. Yeah, I want to write this right here. So let's call it f of x equals sine x. And what's the domain of f? So the domain of f has been restricted for us. We're going from negative pi over 2 to pi over 2. So just that first little section on the graph we've been looking at. And then what's the range of f? So it goes from negative 1 to 1. That is the range of sine. And we've got one complete section that we're looking at. Okay, we can write that inverse trig function two ways. So what is f inverse if f of x equals sine x? So we briefly talked about inverse functions when we were solving for angles earlier in this chapter. So there are two ways that you can write inverse sine. So like this is what our calculator shows us. You would read this as inverse sine of x. So that's one way to show that notation. Or another common way that will also get used on our AP exam is to call it arc sine of x. The arc has to do with an arc length and a central angle, looking at this from the unit circle perspective. So just know that you read it as arc sine, and arc sine means the same thing as inverse sine. So those two things are interchangeable. And what's the domain and range of this inverse function? So I have the domain and range of f, so all I have to do to get the domain and range for the inverse is flip these. So the domain for f inverse will be negative 1 to 1, so it'll be trig values. And the range for f inverse will be negative pi over 2 to positive pi over 2, including both ends, and those are the angles. So for a normal trig function, we input angles and we get out the trig values, the ones that are around our unit circle. But for the inverse, we're inputting trig values and getting out angles that make that trig value happen. All right, so same idea with the cosine graph. If we're graphing cosine, the entire graph of cosine across all real numbers fails the horizontal line test. But if we just pick out a section from 0 to pi, you get the whole range of the cosine graph, and it passes the horizontal line test. So if f of x is equal to cosine x, if we restrict the domain of f to be 0 to pi, then we'll have an inverse function. And the range of f would still be -1 to 1. It still hits all of those values. So the same notation for inverse cosine as well. So f inverse in this case could be written as inverse cosine of x or arc cosine of x. And they're read the same way. The domain of this inverse function, it's not the same. Well, it is the same. Sorry. The domain is the same. It's the range of f becomes the domain of f inverse, but the range is different because we took a different section for the domain between sine and cosine. So the ranges are different too. So this range is 0 to pi. All right, let's do our third trig function. Let's look at tangent. You can also, side note, you can also write arc cosecant, arc secant. Excuse me. We don't need to know about those graphs, but we can evaluate those, and we'll look at that in our examples. All right, we've been graphing tangent x, so let's sketch the graph of y equals tangent x, and let's do it on this interval. So let's just get our parent function tangent x. So we're going to go between positive and negative 3 pi over 2, but remember the first period of the tangent graph is between pi over 2 and negative pi over 2. That's where it has vertical asymptotes. So let's sketch one branch of the period. It's got a point at 0, 0, and then at positive and negative pi over 4, we go up to 1 on the right, down to -1 on the left. And because the period is pi, if I add pi, that's where I land at 3 pi over 2. And we get another period of tangent. And since I'm supposed to go to -3 pi over 2, same idea. -3 pi over 2 would be the next period on the left. So another period of tangent. So if we use a horizontal line across this window, we fail the horizontal line test. But each individual branch passes the horizontal line test. So if we restrict the domain to let's just call this like the first or the original period, if we just restrict between negative pi over 2 and pi over 2, this one branch passes the horizontal line test. So let's let f of x equal tangent x, but we're going to restrict the domain of f to be between negative pi over 2 and pi over 2. Now, I'm not including those endpoints like I did for the other two graphs because tangent is undefined at negative and positive pi over 2. And then what's the range of this branch of tangent? Well, it goes across all real numbers. And so for our inverse function, the notation's the same. You can either use inverse tangent or arc tangent. Inverse tangent and arc tangent, by the way, this is the most common inverse trig that we see for AP calculus, whether you're in AB or BC. So this is one we'll use a lot. And the domain and range would just switch. So the domain for F inverse should be all reals, and the range for F inverse should be between negative pi over 2 to pi over 2, but not including those. So I've established domain and range and what the equations look like. So let's take a look at these three graphs, arcsine, arccosine, and arctangent. What do these graphs actually look like with these domains and ranges? So that's on the next page here. So taken from our textbook here, we have, these are our parent functions for arcsine, arccosine, arctangent. I have seen in AP Classroom a few problems that practice transforming these graphs, like shifting them up, down, or whatever. So we will practice that in a couple of days. But these are the graphs. So again, same domain and range that we've established. If you notice, it's sort of a rotation. Like take a look at the section of the sine graph we have. The concavity of that kind of looks like an S right there. And then this has sort of been reflected a bit, I guess. but that's just because you flipped your x and your y. So this should be a reflection across y equals negative x. Here's arc cosine, here's arc tangent. I want to point out arc tangent, arc sine and cosine have endpoints. They do not go on forever, but arc tangent does go on forever. And as it goes on, the limit as x approaches infinity, just to pull out some old notation here, of arc tangent x. What is this graph approaching? It's approaching this horizontal asymptote, pi over 2. Again, this is something we use in calculus a lot. So just knowing that as you go on, this arctangent graph approaches pi over 2. And the limit as x approaches negative infinity of arctan x is equal to negative pi over 2. So as this graph goes on, it will continue to approach its horizontal asymptote, which is different on the left than it was on the right. All right, what are we focusing on today? Not the graphs today. We'll focus on that tomorrow. Today, I just want to be able to evaluate these. So evaluate each inverse trig expression. Every problem has only one answer, and every answer is an angle. So here's how I do these, sort of a visual for myself. If I want to figure out what's the arc sine of 1/2, first of all, my answer is going to be an angle. So I need to know that. Remember that the range for arc sine is restricted to, let's draw this down here where we have room. The range for arc sine and for arc tangent, the only answers we can get out of arc sine and arc tangent are values between plus and minus pi over 2, right? That's the range for both of those. So let's sketch, because we use the unit circle so often, let's visualize where that range of angles would be. So pi over 2 is at the top. Negative pi over 2 is at the bottom. We don't usually think in negative angles, but that's common for our arc trig. So we don't want to call this 3 pi over 2. And remember, on this section of the unit circle, if we're not using a calculator, we've got 3 angles in quadrant 1, and we've got 3 angles in quadrant 2. And how about we just go ahead and write our, just for quadrant 1, let's just write our trig values. Let's write them correctly. 1/2 radical 3 over 2. And this angle is pi over 3. This angle is pi over 6. I think we know that one's pi over 4. Now, this angle down here is negative pi over 6. This one's negative pi over 3. We're not going to say 11 pi over 6 or 5 pi over 3 or any of that. All right, so back to this question. Arc sine of 1/2 means sine of what angle equals 1/2? And you're only allowed to choose out of this group. So which angle makes sine equal to positive 1/2? Sine's positive 1/2 right here. So that angle is pi over 6. So the answer for theta is pi over 6. This is not the same as what we did earlier in the chapter where it was like, okay, sine's positive in 2 quadrants. What are the 2 answers? If the original problem is just evaluate arc sine or inverse sine or whatever, you're just giving one answer. You're not thinking about which 2 quadrants are you in. Out of these 2 quadrants, which answer does this fall in? Okay, so same idea, arc tangent. Arc tangent of -1 is equal to an angle. Our job is to figure out the angle. What angle makes tangent equal to -1 out of this limited set of choices? Because this is the range for arc tangent. Well, I know tangent's equal to 1 at pi over 4, but it would have to be equal to -1 at negative pi over 4. Because you're down there in quadrant 4, and you get radical 2 over radical 2, divide those out, one of them's negative. Arc cosine, inverse cosine of radical 3 over 2. Again, we're looking for an angle. What's the angle that makes cosine radical 3 over 2? Now, arc cosine is not from negative pi over 2 to pi over 2. Its range, let's go back to this graph, is 0 to pi. So we're only allowed to look at the top half of the circle for our set of answers, from 0 to pi. So I'm not going to label these coordinates again, but same idea. So we can go anywhere from pi over 6 to 5 pi over 6, 0 to pi. All right, so back to the question. When is cosine radical 3 over 2? All right, well, that's happening at pi over 6. And this is positive in quadrant 1. So it's pi over 6 instead of 5 pi over 6. Because at 5 pi over 6, we'd be at negative radical 3 over 2. All right, so this is pi over 6. Basically, if it's an inverse trig function of a positive number, you should be in quadrant 1. Otherwise, your answer will be a negative angle or a quadrant 2 angle, depending on the inverse trig function. Inverse sine of negative radical 2 over 2. So what angle makes that happen? So inverse sine, you're down to these two options. We know it's pi over 4, but it's got to be negative pi over 4 to make sine equal to negative radical 2 over 2. Another trick you can remember, if it's arctan or arcsine of a negative, your answer should be negative. Arc cosine of negative 1/2. So I can see that the x-coordinate is 1/2 at pi over 3, but I want negative 1/2. So that means I must be in the pi over 3 angle that's over here, which is 2 pi over 3, because that's where the coordinate is negative 1/2 for the x-coordinate. So the answer for this one, the angle that we're looking for, is 2 pi over 3. So there's really not a lot of work to show for these. You're just figuring out which angle makes this trig value happen. Arctangent of 0. So again, what theta makes tangent equal to 0? So arctangent, we're down here. Y over x, remember, this is saying tangent of what equals y over x. Now, we know tangent is undefined at positive and negative pi over 2. So the answer has to be at 0 radians, because y over x would be 0 in that case. So this one's always confusing. Arctangent of 0 is 0. So when the trig value is 0, the angle is 0 as well for that one. And then what if I give you some of the reciprocal functions? So arcsecant of 2, you can leave it like this if you want, or you can also say, change it to arcsine and take the reciprocal of that number. I think better in terms of sine, cosine, and tangent. So I like to flip the value inside of the inverse trig and just go from there. So what angle makes sine equal to positive 1/2? That's pi over 6. Arcsecant. So let's make this arc cosine. And if arcsecant is 2 radical 3 over 3, we should know this from our speed quizzes by now. That is the reciprocal of radical 3 over 2. And then it got rationalized. So you need to quickly make that connection. When is the x-coordinate radical 3 over 2? For arc cosine, I'm on the top of the circle. So in quadrant 1, that happens at pi over 6. So all of my answers, when I evaluate inverse trig, all of my answers are angles. Now, the way to make this a little trickier is to use composition. So what if we compose arc trig with regular trig? So the challenge on this is keeping everything straight. Remember, with composition, no matter what the function is, the rule is to work on the inside first, simplify the inside, and then do the outside. Okay, so simplify the inside first. Here's what I like to do. Make a note whether this inside part is the answer here theta, or is it like a speed quiz question. So if I see arcsine, I'm supposed to get a theta out of that. So let's rewrite the problem. It's tangent on the outside. Tangent of what? What is the theta that makes sine equal to 1/2? Sine is 1/2 when theta is pi over 6. So I've taken care of the inside. Now this is just a speed quiz question. What's the tangent of pi over 6? To remind myself that this is speed quiz, I'm going to say, okay, that's y over x, because this doesn't say inverse tangent, it's just tangent. What is the y over x at pi over 6? So if we want to, let's put in our quadrant 1 coordinates just to have something to reference here. I'm not going to bother with the pi over 4. We know what that is. Okay, so y over x at pi over 6 is 1 over radical 3, and then we always rationalize that. Radical 3 over 3. So the tangent of the arcsine of 1/2 comes out to radical 3 over 3. Now we're using the opposite thought process here. So still start on the inside. This is not inverse trig though. This is a speed quiz question. What's the cosine of pi over 2? So remind yourself, you're looking for the x value at pi over 2. The x value is 0. So rewrite this problem. So you've got inverse sine of, instead of cosine of pi over 2, simplify that to 0. And then here we're looking for theta. Arc sine of what is equal to theta, or arc sine of 0 is equal to what theta? So when is y equal to 0? At 0. So theta equals 0 for that one. Start on the inside here. Arc sine of 1. So I should be looking at an angle here. So tangent of what angle? So what angle makes sine equal to 1? Sine is 1 at the top of the circle, pi over 2. What's the tangent of pi over 2? What's the y over x of pi over 2? 1 over 0 is undefined. Or maybe you remember from our graphing unit that that's where an asymptote is. Either way. Okay, start on the inside here. Cotangent of 7 pi over 4. So let's see. Cotangent of pi over 4 is 1. 7 pi over 4 is in quadrant 4. So the inside should simplify to negative 1. Cotangent is negative in quadrant 4. And now we're going to figure out what's the arc cosine of negative 1. So reminder, this is an angle. That's our final answer. What's the angle that makes arc cosine negative 1? Remember, arc cosine is only on the top of the circle. So the angle that makes the x coordinate negative 1 is pi. Okay, number 13. Starting with inverse trig, so we're going to get a theta first. So this is cosecant of what theta? So what angle makes sine equal to negative radical 3 over 2? If it's negative, it's a negative angle. Remember, we're only allowed to be in this bottom portion of the circle here. And instead of pi over 3, we're going to call it negative pi over 3. So remember, we're not using 5 pi over 3. We're sticking to the arc sine rules that say anything between negative pi over 2 and pi over 2. Now this is a speed quiz question. What's 1 over y, because that's cosecant, at negative pi over 3? So at negative pi over 3, you're down here, right? We just said that the sine of that value, let me write that coordinate, sorry. At negative pi over 3, we're at 1/2 negative radical 3 over 2. So that's the sine value. What's the reciprocal of that? It's negative 2 radical 3 over 3. Okay, last example. Cotangent of 5 pi over 4. So this is trig, speed quiz, x over y. So arctangent of, what is the cotangent of 5 pi over 4? So hopefully you've picked up by now that tangent and cotangent of the pi over 4s are 1. And then the question is just, is it positive or negative? So this is in quadrant 3. Cotangent is positive in quadrant 3. So now we're looking for what's the arctangent of 1. All right, remember that's an answer for theta. That's an angle. So what angle makes arctangent 1? Pi over 4. This can be confusing because you're switching back and forth between trig values and angles. So it just takes a little bit of practice. But also if it helps, you can cover up the outside part and just work on just the inside first, get that answer, and then apply the outside part. Sometimes people see both at once and that gets confusing. So we can practice this a lot. So come in and see me for office hours if you want more practice on this.